Welcome back. We're going to introduce two new derivative rules. One is the derivative for the sine function. The derivative of sine is just cosine. And the derivative of the cosine function. Derivative of cosine is negative of sine. I'm going to prove both, and I'm going to start with the derivative of sine, and you'll notice I've got some things already written down up top. One of them is the angle sum formula for sine, and the other is a couple of special limits that we've used before in chapter 1. As it turns out, I'm going to need both of these things to be able to complete my proof. So if I'm looking for the derivative of sine of x, so that would be my limit as delta x goes to 0 of sine of x plus delta x minus sine of x all over delta x. So right away, I'm going to be using the very first identity here, which is the angle sum identity for sine. You can see that I have that sine of x plus delta x, and so I'm going to use that formula to rewrite that. Instead of sine of x plus delta x, I'll have sine of x cosine delta x plus cosine of x sine of delta x, and then I've got a little minus sine of x at the very end of it all. Okay, so one thing that we might notice here is that I've got, if we're thinking about the identities that we have, if I had a sine of delta x over a delta x, that would be good because I know the limit for that would go to 1. And if I had a 1 minus cosine delta x over delta x, that would go to 0, which would also be kind of helpful. And I can actually make both of these happen with just a little bit of rewriting. So first thing I'm going to do here is I'm going to take my two terms that I have in the numerator that involve the sine x. You'll notice the very first term, I've got sine x times cosine of delta x, and I've got a minus sine x. If I were to take out a sine x from both terms, that would leave me a cosine of delta x and a minus 1, which is not quite what I want. I want a 1 minus cosine of delta x. So to make that happen, instead of taking sine of x out of both terms, I'll take negative sine of x out of both terms. So that means from the first term, I'll have a minus cosine of delta x left over. And from the minus sine x, I'll have a positive 1 left over. From the middle term that I have, I'll just leave it as it is. I've got that cosine of x times sine of delta x. And now what I'm going to do is split this up. I have two fractions that I'm going to make out of 1. So I'm going to take that first part of that numerator all over delta x. And then I'll have that second part of the numerator also over delta x. Now, one thing that we know, we've got some limit laws that we can use to help us out, and one of them is if we have two terms and if the limit exists for both terms, then the limit is just the two limits added together. Further, we've got if I have a limit existing, then a constant times a limit still exists as well. And if you're looking at this, the minus sine of x does not involve delta x at all. So that's essentially like a constant. Essentially, I can imagine this as a constant times 1 minus cos delta x over delta x. That's where the limit is. And similarly for the second term, the second fraction, cosine of x, there's no delta x there, so essentially I'll treat that as though it were a constant. I'll have cosine of x times the limit of what's left over. And now I can say, great, both of those limits exist. They are both things from my little limit laws. The 1 minus cos delta x over delta x, I know where that goes. That goes to 0. Sine delta x over delta x, that goes to 1. So I have minus sine x times 0 plus cos x times 1, which is just cosine of x. And there we go. We have our derivative of sine that's been shown. I'm going to do similar sort of things to show cosine, except for cosine, I'll be using the cosine angle sum formula. So for cosine of alpha plus beta, the formula is cosine alpha cosine beta minus sine alpha sine beta. So I'll be doing much the same sort of work here for the second proof. I want the derivative of cosine of x. That's the limit as delta x goes to 0 of cosine of x plus delta x minus cosine of x all over delta x. I'll first split things up using the cosine angle sum formula. So that'll be cosine of x, cosine of delta x, minus sine of x, sine of delta x, then I'm going to do kind of the same sort of thing that I did before, where I'm going to split this into two fractions. So I'm going to say to myself, I notice, same as before, I have two terms that have something in common. The first term has a cosine of x. The second term has a cosine of x. So if I took those two terms and factored cosine of x out, I would have a cosine of delta x and a minus 1 left behind. Of course, I want 1 minus cosine of delta x, so I'll do the same thing that I did before and say from the first term, from the last term, I'll factor out a negative cosine of x. That'll leave me a minus cosine of delta x and a positive 1 left behind. For the second term, I'll just leave it as is, the sine x, sine delta x. And everybody will be all over delta x. And this is, of course, limit as delta x approaches 0. Now I'll split it up into two, just same as before. And here I'll be a little bit faster about it because I know I'm going to be basically doing the same steps. I'll say, well, really, you'll have the first part of the numerator over delta x, and the minus cosine of x, that's really sort of treated as a constant. So we'll have minus cosine of x, limit delta x goes to 0, of 1 minus cos delta x over delta x. And then for the second part of it, again, sine of x is going to be treated essentially as a constant. So I'll have minus sine x times my limit, delta x goes to 0, of sine delta x over delta x. And same sort of thing as before, things clean up pretty quickly here because they both are special little cosine and sine identities. The 1 minus cosine delta x over delta x, that goes to 0. And sine delta x over delta x, that goes to 1. So we are left with negative sine of x. So there we go. We've shown the derivative of sine is cosine. We've shown the derivative of cosine is negative sine. And now let's use that. here I've got a function, and I want to find all the places in that interval from 0 to 2 pi where f of x has a horizontal tangent line. And again, horizontal lines have a slope of 0. The slope of my tangent line is the same thing as the slope of f of x, or in other words, the derivative. So I want to find out, where is the derivative equal to 0? If you have a horizontal tangent line, the slope is 0, and if your slope is 0, then the derivative is 0. So I guess first bit of business here, let's find our derivative. The derivative of sine is cosine, and the derivative of cosine is negative sine. And we want to let the derivative be 0 and then solve for x. So I have here 0 is equal to cosine minus sine, which I could rewrite that as sine of x equals cosine of x. So if I'm looking to solve this, I could make my life a little bit easier by dividing both sides by cosine. I'd have sine divided by cosine is equal to 1. Of course, I'd have to make a little note to myself. If you're dividing by something that involves x, then that means there's potentially going to be some values that are being disallowed or being forgotten about, potentially lost solutions. So I'm going to make a note here. If I'm dividing by cosine of x, cosine had better not be equal to 0, or in other words, x should not be pi over 2, and x also should not be 3 pi over 2. So I should be concerned. I should actually check to myself, are those possibly solutions? Is pi over 2 a solution that I'm losing? And it isn't. I can check to see that if I had pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0. Left side and right side are not equal to each other in my equation. Same thing for 3 pi over 2. Sine of that is negative 1, cosine of that is 0. Left side and right side are not equal to each other. So I don't have to worry about me losing solutions here. It's been fine. I can divide both sides by cosine of x. I know that that means that pi over 2 and 3 pi over 2 are excluded, but that doesn't matter because I've checked to see neither of them are solutions. So now what do I have? Well, I've got tangent of x equals 1, and I know that there's two places where tangent is equal to 1. One of them is pi over 4. That's the angle that's in quadrant 1, where tangent is 1. And I also know that tangent is going to be positive 1 over in quadrant 3, where the reference angle is pi over 4. That will also be a solution, or in other words, 5 pi over 4. So I've got two different x values. And again, I've said this a few times now, but worth mentioning it. When I say find all points, that means find all x and y points. So we've done some of our work, but not all of it. I've figured out for myself where are my x and y points, where are my x points, but I haven't figured out what my y values are yet. So now I need to go back and find out what is my y value. So when x is pi over 4, the y value is f of pi over 4, which is sine of pi over 4 plus cos of pi over 4. Or root 2. So one of the points is the point pi over 4 root 2. For the second point, that would be when x is 5 pi over 4. The y value would be f of 5 pi over 4. And that would be sine of 5 pi over 4 plus cosine of 5 pi over 4, which is negative root 2 over 2 minus another root 2 over 2, or negative root 2. So that means that our second point happens to be 5 pi over 4 negative root 2.